this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am going to deal with the course Computational Aerodynamics, and the topic is Introduction to Finite Difference Method. So let's recap in short. So what we had seen in the previous lectures. Okay, we had seen what is CFD and why it is very important. Okay, and we had seen what are the steps involved in the CFD, and how can you choose a particular type of problem, how can we apply boundary conditions, and how can we use the grid generation and all other techniques. And we had seen what are the governing equations used in the CFD. So we have continuity equation, and we have momentum equation, and we have energy equation. So in short to say, so these equations 1 and 2 and 3, basically these are written in the vectorial form. So if you write in the scalar form, so this momentum equation will be split into 3. So you have u velocity momentum, v velocity momentum, and w velocity momentum. So 1 plus 3, 4, and energy 5. So total 5 equations would be there, or will be there. And one more thing, the number of variables that we have actually are greater than the number of equations. So in that case, what we do is like we will take some assumptions for the flow, whether it is steady or unsteady, steady or uniform. So these assumptions we will be taking or implicit, and based on that, the equations will get reduced actually. So that number of equations and number of variables would come near to equal, will be equal, and a closed form of solution is obtained. So if it is not, then we will be using additional equation. Let's say P is equal to rho RT for a compressible flow. Whereas here you can see, if you have the flow as incompressible, the density term will come out and the equation will get reduced. Okay. So this is what we solve for the CFD. Based on the type of problem we have, so we will actually take the CFD approach. And these are the flow, external flow and internal flow. Then after we have Lagrangian and Eulerian approach. So the particle tracking mechanism is nothing but your Lagrangian approach. And if you calculate the flow properties for a given average, so here you can see the average properties if you're calculating at a particular cross section, so that would give the Eulerian approach. So you have types of grid, you have structured grid. So as I told you, if you take the grid, so the entire circumference, so the circumference part, whatever it is enclosing, it is called domain. So here the domain would be like you have the rectangular one. So this is the domain. So the domain is the area of interest where we have to see the flow analysis, fluid flow analysis or heat transfer problem. So whatever the thing that we are measuring. And inside the domain, you have different segments. So we have a closed entity which is called cell. Okay, that cell is the entity which is present inside the domain. So that cell will be consisting of a point called grid point. So the intersection of these X lines and Y lines. So basically the X lines are the lines which are parallel to the X axis, and for the structured grid, so these no two X lines will meet each other, and whereas for Y axis also those two lines will not meet each other. So the intersection of both X and Y is called the node point or the grid point. So the combination of these, if you join lines of different node points, then you would get a shape called a cell, and this is called node cell or grid cell, whatever we say. And here the cell is made up of 4 sides, and for a structured grid, basically the 2D one you have a quadrilateral, and or for the 3D grid you will have a hexahedral. Okay, whereas here you can see the grid points are uniformly placed. So basically the successive distance between two grid points so is same, then it is called uniform. And one more thing, we are getting calculated, or we are calculating the equations, governing equations which we have, the continuity equation, momentum equation, energy equation, at the center of the cell, or we will calculate at the node point. Okay, so the node or the grid point are nothing but the intersection of x and y lines. So this is nothing but the node or grid point. Okay, and the centroid of the cell is called cell centered actually. So this is what we have. So if you take the zoom view, so here you can see this is nothing but your grid. Okay, this is a grid point. Okay, fine. So the distance here, delta x. So here also it would be delta x. So here also it would be delta x. So delta x, delta x, delta x. So the spacing is same. So that's why, so we call it as a uniform mesh. If spacing is not equal, then we call it as non-uniform. So this is called your edge length. Okay. So basically for the 2D, so this is called your edge length, which will give the flow which is passing like this. And if it is finite difference method, you will be calculating governing equations at this point. If it is finite volume method, you will be calculating equations at the center of the cell. Okay, this is what we have the non-uniform mesh. Okay, so non-uniform in the sense, here you can see the distance is different, and if you observe, the distance is different. So the distance between two grid points, if you see at the origin here, it will be less. Here it will be more. Okay, so this is nothing but your non-uniform spacing. So this non-uniform spacing can actually vary both along x-axis and y-axis. So you can take either x-axis, or you can take either y-axis, or you can take combinedly both x and y-axis. So here you can see you have both x-axis and y-axis spacing vary. So this is the example. And one more thing, what we have discussed, like you have the coarse and finite grid. So the meaning for the coarse grid is like you have only less number of points. Finite grid is nothing but more number of points actually. So why we are taking this? Because let's say if you are doing analysis over a flat plate or any other phenomena. So if you are varying the grid points, so let's say initially you have 1 million grid points, and you have obtained a solution, let's say as 2 meter per second. So for 2 million grid points, if the velocity is varying, let's 2.4 meter per second, then you cannot use 1 million grid points. Why? Because as the number of grid points are varying in the domain, so you cannot use that particular grid points for the other solutions. First, you need to actually do the grid independent study or the mesh independent study, which will define that after certain particular grid points, the solution will not vary, even though you keep on increasing the grid points. So let's say what we have is like 2 million cells, you have 2.4 meter per second. If you are using 3 million, so if you have 2.41 meter per second, and if you have 4 million, even if you have 2.41 like that meter per second, so like this. So this is what you have. Fine. So 2.41, 2.4. So this is what we have. So basic entity is like, so the computational cost for 4 million will be higher, and 3 million would be lower somewhat, and 2 million will be very lower. So what is happening? Even at the lower grid points, you are able to capture the solution, okay, which is near to the experimental value. Then that sort of grid points you can use. So no need to go for higher number of grid points where you will have 3 million and 4 million. Okay, so this is what the meaning of mesh independency. So the meaning is like, so even though still if you keep on changing the number of grid points, if you are changing the grid point, the solution will not vary. Okay, so we need to use the minimum number of grid points where the solution does not vary, even though if you are increasing the grid point. So after doing that mesh independency study, then you can implement for your model. Okay, and here you have unstructured grid. So basically, what is unstructured grid? So the difference of structured and unstructured is, so here you can see the cell is triangular for 2D. Okay, so for 3D it would be tetrahedron. Okay, So what is happening here? The unstructured grid, you can see that the cell is formed of 3 points, let's say 3 node points. Okay, and for a particular node point, there are so many number of neighboring node points. And the advantage of and disadvantage of the unstructured grid is, for the unstructured grid, so the mesh performance actually will depend upon the type of geometry. And if it is a complex geometry, you can go for directly unstructured grid. If it is a regular and simple geometry, there is no need of unstructured grid. Why? Because the grid points or the mesh points, when you compare with the structured and unstructured grid, unstructured grid will have more number of mesh points. Therefore, if for a simple geometry cases, let's say flow over flat plate and flow over cylinder, so these small objects and simple cases, you can use the structured grid. So there is no need of going for unstructured grid. And one other important thing is that the structured grid actually is applied for regular operation. For complex geometry, there is some problem. You have to take more attention and special care to perform the structured grid for complex geometry. And here you can see, so the coarse mesh and finer mesh application. So near to the wall, you have a very fine region, and this is called actually boundary layer. To capture the boundary layer, we'll use more number of grid points. And why? Because here near to the wall, you have boundary layer and the viscous region. So these effects has to be studied. And apart from that, away from the far field, you have this region where your flow field, actually what happens, it is called inviscid flow. So coarse mesh is enough actually. So this is fine mesh, and here it is coarse mesh. You can actually have the hybrid grids, which is combination of structured and unstructured grid. So some regions where you have the complicated things, geometry, you can apply unstructured mesh. And the other regions where it is easier, you can go for structured mesh. Okay, that is nothing but the hybrid mesh. Okay, and coming to fluid flow analysis, so there are different types of approaches. So here you have finite control volume, which is fixed in space, and finite control volume, which is moving with the flow. Okay, and one more approach is like the fluid element, which is fixed in space, and the fluid element which is moving along the flow. Okay, so the difference is like there are two forms of governing equation. So one is conservative form of governing equation, other one is called the non-conservative form of governing equation. So the continuity and momentum and energy equations will be derived for different types of control volume. So the control volume is nothing but the entity where we will be seeing the fluid flow analysis and derive equations and solve that. Okay, so how the flow is entering the control volume and how it is leaving the volume. So what is the rate of accumulation inside the volume and what changes are happening and what effect is happening. So this is what you see. So if you take an example of an aircraft engine, let's say, so here the flow is coming and entering the engine. So you have the compressors here, and here you have the combustion chamber. Here you will have turbine. Here you have nozzle. So this is what you have. So basically what happens when the flow is entering the engine, so here the velocity will be changing, and how the changes are made inside the control volume, we need to actually study that one. So if you are taking some X amount of flow inside the engine, so what are the changes made inside the engine for the flow, and how it is coming out of the engine, with what velocity, with what pressure and what temperature it is coming. So we need to actually study that thing, and what are the effects that is coming on the engine, we need to see. So this is what the small example. Okay, so where you can see about control volume approach. Okay, so control volume is nothing but entity where your area of study is limited to certain region, and then you can actually extend. So how I'm saying is like, let's say you have a flow arbitrary in a space, so you can draw control volume of any shape. So there is no actually a requirement that control volume should be in this shape. There is a restriction of this shape, that shape, it's not there. So you can use any shape, the control volume, and you need to actually see what are the effects. Okay, the flow which is entering and leaving, accumulating. Okay, so this is what we have. Fine. And the other approach is like here it is moving with the fluid. So when the flow is coming inside and leaving outside for a control volume which is fixed in space, so the rate of accumulation or the rate of decrease of flow inside the control volume will be equal to the flow which is leaving the control volume. So with that you will get the conservation of mass equation, then rate of change of momentum, the forces acting on the control volume will get momentum equation, and the work done on the control volume and work done by the fluid and the heat transfer phenomena will get the energy equation. So when you derive governing equations for a finite control volume which is fixed in space, then those sort of equations are present in integral form. Why? Because we will integrate over the control volume. So the fluid, if you are, the flow will be going here, 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 everywhere in it will be going. Everywhere you have inlet. So what you need to do, you have to integrate actually. So we will actually generate the integral form of governing equations. Okay, and if the control volume is fixed in space, then that sort of equations that we derive is called conservative form for only fixed in space cases. So when this control volume is moving with the space or moving with the flow, then we derive a form called non-conservative form of governing equations. Okay, so this is called a conservative form and this is called the non-conservative form of governing equations. Okay, and for the both approaches A and B, so this is what this A which is control volume fixed in space and control volume moving with the space. So we are deriving the integral form of governing equations. For the B part, what we have is like, so the fluid element is moving with the flow, and here what is happening, here we will derive the differential form of governing equations. So fluid element, whatever it is there, so what are the rate of molecules that are passing through the fluid, so these things we will be seeing. And for this case, for the fluid infinitesimal fluid element approach, we will derive only the differential form of equations. If this fluid element is fixed in space, then what happens? Your equations which you have derived would go for the conservative form, but they are in differential. Okay, and the fluid element which is moving with the space, then you are deriving an non-conservative form. Okay, and they are differential equations. Okay, so these are the approaches actually how we will derive equations for the fluid flow analysis. Okay, and now we'll be seeing actually what is finite difference method and how we will represent them in mathematical form. How we can see the structured and unstructured. So let's say structured grid, how the finite difference method is solved. We'll see. So before that, I would like to actually give the terminology of finite difference method and then go for the equations. Okay, so let's actually draw the domain, let's say, and let's draw here x lines, and let's draw y lines. Okay, so let's say this is let us draw the coordinate axis also. This is x axis and this is y axis. Okay, so let's, what is this point called actually? Let's say this is 0 comma 0. Let's say origin. So here you have 1 comma 0, here you have 2 comma 0. Okay, and similarly what would this one, 0 comma 1 and 0 comma 2. Okay, and 0 comma 3. Fine. So what would be this point then? 1 comma 1, and here it would be 1 comma 2. Okay, so what would be this point? So this will be 2 comma 1, and this would be 2 comma 2. Okay, so basically what we are doing is like, so we are replacing this x terminology in the finite difference method, x as I and y as j and z as k. Okay, so when you're taking an area of interest here, let's say, so for a 2D axis, let me draw here the zoomed one. Okay, so let's say this is our point of interest. So if you are writing these as 1 comma 1, let's say, okay, so let's say this is my point. So actually here these are called the boundary points. So the boundary points, so the boundary condition would give you the values at the boundary edge. So therefore no special attention is required. Why? Because when you are initially starting the simulation, you would assign what is the velocity or what is the temperature, what is the pressure along these boundaries, or pressure, sorry, temperature, velocity, these aspects at the boundary. And for the boundaries, like you will have values. But so these are called the boundary nodes. See, the grid points which are associated with the boundaries are called the boundary points or the boundary nodes. And inside the domain, these are called the interior nodes or inside points. Okay. So if you are concentrating on the inside point, let's say, what happens? So you have these points. Okay. So let's say what we have, you have a continuity equation. What is the continuity equation of 2D? So incompressible du by dx plus dv by dy is equal to 0. So in finite difference method, what we are doing is like, so we will replace this partial differential form and make it in algebraic form and solve those equations. So how we are doing, we'll be seeing. First thing, the terminology is like, so let's take this point as I comma j. Okay, so if this is called I comma j, so what would be the next point here? This one is called I plus 1 comma j, and the left one would be I minus 1 comma j, and the top one would be I comma j plus 1. Next, the bottom one would be I comma j minus 1. So this is what you have: I plus j I comma j plus 1, I comma j minus 1, and I plus 1 comma j, I minus 1 comma j. So this is what you have. You have 4 neighboring points for this given grid point, which is I comma j. So one which is along x-axis, one which is along y-axis. Okay. So du by dx plus dv by dy is equal to 0 is the continuity equation which we have. So we are trying to replace, or we are replacing this in the index form actually. So how we will write, we will be seeing. So what would be like du by dx? So let us write in this form, which is u2 minus or u1 divided by delta x plus v2 minus v1 by delta y. So this is how we write in the crude form. Okay. So in the finite difference form, there are two things. One is like forward difference. Other one is called the backward difference. Other one is called the central difference. Okay. So the meaning of forward difference is, if you are finding any value with respect to I comma j and I plus 1 comma j, and what do you have, I comma j and I comma j plus 1. So let's say, so these entities will come under forward difference. Okay. So if you take particular point, this point, and if you are marching towards the right, okay, so this is called the forward difference. Okay. If you are taking the points into consideration of I plus 1 or j plus 1, then that would constitute to finite difference method of a forward one. Okay. So the backward one would be like, what do you have? The backward one is like I comma j and I minus 1 comma j, here I comma j and I comma j minus 1. So this is like along x-axis and this is like along y-axis. Okay, so if you are taking the points which are backward, so here you can see I comma j and here it would be I minus 1 comma j. Okay, so if these 2 points are taken into consideration, then that would go for the backward difference. I think so. About this I comma j, so which point? So the I comma j is the reference point. With respect to the reference point, the meaning of forward is going towards rightwards. So which is of I plus 1, I plus 2 like that. If you are going for backward, then it is called I minus 1, I minus 2 like that. Okay. So what is the meaning of central difference about this point? Then that would go for I plus 1 comma j and I minus 1 comma j, and then after I comma j plus 1 and I comma j minus 1. So let's say this is I comma j point. So about this point, the central difference, so what we are taking is like you will take one point which is on the left side and one point which is on the right side actually. For the forward difference, you will take the I comma j point and the right point. For the backward difference, you will take the I comma j point and the backward point. But for the central difference, what we will be taking? We will be taking the I plus 1 comma j point, the forward point as well as the backward point. So let's say what is happening, the distance between the I minus 1 comma j and I comma j is delta x, and here I comma j and I plus 1 comma j is again delta x. So the addition would give you 2 delta x. So the spacing for the central difference will give you 2 delta x or 2 delta, and for the spacing of finite forward difference and finite backward difference method will give you only delta x. Why? Because only one step. So this is called the stencil size. Stencil size. Okay. So if we write down, so what we are doing actually, so you have du by dx plus dv by dy is equal to 0 we have. So what we are doing, so we are replacing this. So for the crude approximation, you have u2 minus v1 by delta x plus v2 minus v1 by delta y is equal to 0. So we are replacing this by index notation. So what we are taking is like, so the velocity at I comma j would be u of I comma j, and the velocity at I plus 1 comma j would be u of I plus 1 comma j. So for the forward difference, what we have, so that would go for, so u of I plus 1 comma j minus u of I comma j divided by delta x. So this is of du by dou x term. Plus one more thing, what do you have? So you have y velocity. Okay. So therefore here you can see the difference for the x derivative. So for the x velocity, you can see that j index is not varying. Why? Because for the forward difference along the x-axis, your I value will vary. So why? Because this is dou u by dou x. So this variation is along x-axis, not y-axis. So therefore, this I index notation only is varying, not j index is varying. Okay. So when you go for dou v by dou x, then what happens? This would give you, so let's say v of, okay, or you can take u. So you can actually, what we do is like you will be taking as u. Why? Because index notation is there, and u of I comma j plus 1 minus u of I comma j divided by delta y. So this is what we have. Okay. So these are the terminologies which we use. Okay, is equal to 0. So for the grid donation. Okay. So if you take, what happens, like if you take common, like what happens, this will get into linear form. So you will have the variables of u of I plus 1 comma j. So u of I comma j and u of I comma j plus 1. So you have 3 variables for a forward difference. Okay. So this is what the meaning of forward difference method. Okay. For the backward difference method, what we have, we can write actually. So what finite difference method is doing, like, so we are actually replacing this partial derivative terms dou u by dou x, dou v by dou y in form of the what is it, discretized form, and those discretized form we will actually convert into algebraic equations, whatever the things we have, and put in a form of matrix and solve it. Okay, so this is what we have it, right? Now, so what we are doing is like the backward difference. For the backward difference, so you will take u of I comma j minus u of I minus 1 comma j divided by delta x plus u of, sorry, this is delta y actually. So if it is like only I is varying, it is delta x, sorry. And here u of I comma j minus u of I comma j minus 1 divided by delta y is equal to 0. So this is what we have. Okay, so one thing is like you have delta x, another thing is like your delta y. Okay, so the thing is the backward difference. So what is backward difference? Here what we have is like the I comma j and I minus 1. Here I comma j and I comma j minus 1. Okay, so for the forward difference you have I plus 1 comma j and I plus 1 comma j comma I. Next you have j plus 1 comma j plus 1 comma j. Okay, so this is for forward difference. So for the end, like you, if you see the central difference, what would you have? So u of I plus 1 comma minus u of I minus 1 divided by, what is stencil size? So delta x, so 2 delta x plus u of what do you say, I comma j plus 1 minus u of I comma j minus 1 divided by 2 delta y is equal to 0. So this is what you have. So this is of central difference. Okay, so let's compare actually all the three entities. So what we have. Okay, so what we are doing is like if you see the forward difference FD, this is forward difference, this is backward difference, and this is called central difference. For the forward difference, the equation is like this. So u of I comma so u of I plus 1 comma j minus u of I comma j divided by delta x plus u of I comma j plus 1 minus u of I comma j divided by delta y is equal to 0. So this is what you have for forward difference. For the backward difference, what do you have? U of I comma j minus u of I minus 1 comma j divided by delta x plus u of I comma j minus u of I comma j minus 1 divided by delta y is equal to 0. This is what you have for backward difference. For central difference, what do you have? U of I plus 1 minus u of I minus 1 divided by 2 delta x plus u of comma j, u of I comma j plus 1 minus u of I comma j minus 1 divided by 2 delta y is equal to 0. So here you can see the comparison of all these three schemes, like forward difference scheme, backward difference scheme, and central difference scheme. Okay, so what we have here for the forward difference scheme, so you have I plus 1 comma j point and you have I comma j point. Okay, and here you have I comma j plus 1 point, here you have I comma j point. Okay, so the variables are like you have u of I plus 1 and u of I and you have j plus 1. So the way, like, these are the things which you have. Okay, so this would be comma j, this would be comma j, this is comma y. Okay, and here also you have the I and I minus 1. Here for the central difference, the thing is that you are capturing both the left side and the right side. So this would constitute to the central difference actually. Okay, so this is called the central difference scheme, and for the central difference scheme, the order of accuracy would be somewhat higher than the forward and backward difference scheme, but the computation time would be higher actually. Okay, so why we are actually taking the forward difference, why we are taking backward difference, why we are taking central difference, because depends upon the type of problem. Let's say if you have the convection problem, diffusion problem, convection diffusion problem, uh, depends upon the type of problem we have. So particular type of scheme is helpful actually to do. Okay, so let's say for the forward difference, so one type of phenomena is helpful. For the backward difference, one type of phenomena, let's say for the forward difference, the convection phenomena is helpful. For the backward difference, the diffusion phenomena is helpful. For central difference, both convection and diffusion is helpful. Let's say I'm giving an example. So what I'm taking is that, let's say you have a flow through pipe or flow through nozzles or any kind of thing. So depending upon the physics of the flow, if you have any backflow or straight, any other kind of thing, so in order to capture those parameters properly, you'll be using that particular type of scheme. Okay, so if it is a forward difference scheme, then you will be setting up properly the convection phenomena. If it is a backward difference scheme, you'll be setting up properly the diffusion phenomena. If it is a central difference scheme, you can study both convection and diffusion phenomena. So this is what we have. And one actually advantage is that for the finite difference method, so you will be able to do the simulation for a simple object, actually, in the sense like simple geometries. So we are solving these grid points. Okay, at the grid points you will derive these equations. So what I'm saying is that, so this I index value and j index value will vary from 0 to n, and 0 to, let's say, n. So 0 is nothing but boundary, already you'll have value. Let's say you'll go for 1 and 1. So what is happening? So the indexing number I comma j will give you the position of grid point. So where the grid point is located and what is the value of velocity and these things. So when you are doing these equations, when you're solving these equations, you will be able to get the value of velocity, pressure, temperature at particular grid points. So in the given domain, so what is happening? So if you want to calculate temperature at this point or at this point, the interpolation mechanism is there. But finite difference method will give you the value at this point actually in the fluid free. Okay, so the other aspect of these schemes is like you have order of accuracy. So now if you include the time, okay, so till now we have seen only study terms. Okay, now we have time derivative terms. Let's say you have d rho by dt, okay, and you have del dot rho u is equal to 0. So this is for the continuity equation. And let's say you have the momentum equation du by dt plus what is it, u into du by dx, let's say, or let's say constant c into du by dx is equal to some 0. So let's say we will be doing this equation. So what is happening? So for the time derivative terms, the index would go for n actually. So how would we do is like u of n plus 1 minus u of n divided by delta t, and this one is plus c into, so u for the forward difference method, so u of I plus 1 of particular time step n comma j minus u of I comma j of n divided by delta x is equal to 0. Okay, so here the one more term has come. What is the term? Dou u by dou t. So what is the meaning of dou u by dou t? Actually, this is the time derivative term. For the time derivative term, the indexes will come over the superscript actually, or subscript. So this is the time, and the bottom one here, whatever you have, these are the space derivative terms. Okay, so let's say if you this I come again. Okay, so if you want to find the value of velocity at that particular point for the next time step, okay, so this is what you have, is u of u of I comma j n plus 1. Okay, so and one more thing, these whatever the things that we are writing, so based on the terms which are present in the equation, we will actually discretize those equations. So the time derivative terms and the space derivative terms will be different. If you don't have any time derivative term, that would be steady term. Okay, if you have the time derivative term, then that would go for unsteady term. Okay, so this is what you have. Okay, so there is one more parameter which is called Coarse number actually. So the basic thing is like I would say, so u of this one by delta x is equal to some, let's say, c into comma j divided by delta x. So this is what we have. So if you are sending this delta t here, so what happens is equal to u of I comma j to the power of n plus c into delta t by delta x into, so this is what we have. So this is nothing but the velocity. Okay, this is the velocity at which the wave or the flow is moving, and this is the delta t and the time step what you have, and this is the delta x, the distance between 2 points what we have. So here you can see these are the grid points. Let's say here grid point 1 comma 2 and 2 comma 2. So the delta x is nothing but the grid point distance between 1 comma 2 and 2 comma 2. So on you can. So if it is uniform grid, the delta x will be same. If it is non-uniform grid, the delta x would be different at different points. So let's say here you have 2 comma 2 and this next point is 2 comma 3. So then this would be delta y. Okay, so the coordinate number will be both along x and along y. Okay, so you have cx and cy. Okay, so if the coordinate number is like for only 1D, you will have the coordinate number along x, and if it is coordinate number along y, you have cy. So the combination of this should be less than 1. Okay, so these things we will be seeing in the further class in detail, but when you see the time derivative terms and when you are doing the unstudied problems in CFD, the coordinate number is very important parameter. The important aspect is that, so if you have a cell that would have the distance delta x and delta y. Okay, so and the flow velocity is important. At what velocity the flow is going through the cell and at what time it is going, that is very important. Okay, so basically the coordinate number 1 less than 1 condition is for stable flow actually. So when you take coordinate number greater than 1, then that would actually go for the unstable. Okay, so if it is a 2D problem, the combination of these two should come less than 1, and if it is like a 1D problem, then you have coordinate number less than 1, like which is of c into delta t by delta x. Okay, so this coordinate number will actually play a major role in stabilizing a numerical scheme. If you have a particular numerical scheme or any other aspect, so this coordinate number actually will try to enforce the stability on the numerical simulation while performing it. So basically the delta t, okay, if you take 0.1 and if you take delta x as 0.1, if your velocity is some 0.1 meter per second. So what happens? So the current number would be, so 0.1 into 0.1 divided by 0.1. So that would give you 0.1. Okay. So actually, while doing the simulation, you need to take care of what is the spacing, and if the spacing is fixed, let's say, so you need to play with the time step. So time step can go very small, or time step can get increased based on the core number and based on the uh, delta x phenomena what we have. Okay. So in summary, the core number will play a major role in the time dependent simulations. Okay. So here we had seen the introduction for the finite difference method, and we had seen what are the different methods, basically forward difference and backward difference and central difference schemes for finite difference method. And we'll see in the next class, so what are the derivations made to get this forward difference method. Okay. And what are the derivations made to get this backward difference method? What are the derivations made to get the central difference method? So how do you get the value? So u of I plus, so for the central difference method, what we have, so u plus 1 comma j comma minus u minus 1 comma j divided by delta x. So how did we obtain actually, sorry, divided by 2 delta x. So how did we obtain these things? And one more thing, like how we get values of u of I plus 1 comma j, how can we replace these things? So these all aspects has to be studied. Okay. And in the coming module, we'll be seeing the Taylor series of expansion in replacing these partial derivative terms. Okay. So these things, why we are doing is because you have partial differential equations in the governing equation. So those terms are partial derivative terms. So du by dx plus dv by dy is equal to 0. And let's say u into du by dx plus u into du by, sorry, du by dt, u into du by dx, okay, plus v into du by dy is equal to minus 1 by rho dp by dx. Let's say we have these things. So these all terms are the partial derivative terms. So we need to actually replace these partial derivative terms in the discretized form. These discretized form you should arrange in the form of matrix. Then you need to invert it and get the solution of the particular problem. So this is what we do for the CFD. So based on the type of method we have, so if we are going for finite element method, you'll get the discretized form at the grid points. For the finite volume method, you will see the gradients. Okay. At the center of the cell, you will be actually calculating the values. For the finite volume method, at the center of the cell, you will calculate the values. For the finite difference method, at the grid point, you will be calculating the values. Okay. In the next coming session, we'll be seeing what is the Taylor series of expansion and how we will be able to do or derive the higher order accurate schemes for getting the CFD solutions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.